All right, let's dive right into this explainer and unlock the fascinating, literally non-stop world of chemical equilibrium. Now, you might have grown up thinking chemical reactions are just a simple one-way street, right? Reactants turn into products and then, well, they just stop. But as we're going to see, reality is way more dynamic than that. Think about juggling for a second. It completely shatters that illusion of a chemical reaction simply stopping. Instead of a dead end, we're actually looking at a furious, equally matched two-way street. Reversible reactions are exactly like a couple of jugglers continuously throwing and catching clubs. The action definitely hasn't stopped, but because they're throwing and catching at the exact same rate, the number of clubs in the air, or, the concentration of our chemicals, stays perfectly constant. The forward and reverse rates are just perfectly matched. To keep us on track, here's our roadmap for today. We'll hit the dynamic illusion, measuring the balance, stressing the system, solving with icy tables, and finally, the driving force.
So Section 1. The dynamic illusion, a non-stop world.
Here's the absolutely crucial point. While the measurable amounts of reactants and products look like they've stopped changing to the naked eye, the microscopic molecular action itself, it literally never halts. If you were to zoom way in on a sealed flask of reacting gases, you'd see this chaotic storm of bonds breaking and forming. The only reason the overall concentrations flatline is because every single time a product molecule is formed, another one is instantly broken back down into a reactant. It is just a relentless state of dynamic balance.
Moving right along to Section 2. Measuring the balance, quantifying equilibrium.
All right, so if it's constantly moving, how do we measure it? We use two vital dimensionless numbers that act kind of like our chemical compass. We've got the reaction quotient, Q, and the equilibrium constant, K. Think of Q as a snapshot of our current state. It tells us exactly where the reaction is right this very second. K, on the other hand, well, that's our final destination. It's the ratio of products to reactants when the system is finally settled into that perfect dynamic balance at a specific temperature. And depending on what we're actually measuring, we might use Kc for concentrations or Kp for gas pressures.
Now, according to the law of mass action, we derive this snapshot Q directly from the balanced equation. We just take the concentrations of our products, raise them to the power of their stoichiometric coefficients, and divide all that by the reactants raised to their coefficients. Simple enough, right? As a reaction proceeds, this Q value is going to continuously change. It might start at 0 if we literally only have reactants, or it could be infinitely large if we only have products. But honestly, regardless of where it starts, Q will predictably decrease or increase until it eventually slams right into that magical constant value of K.
Section 3. Stressing the system, Le Chatelier's principle. Enter Le Chatelier's principle. Think of this like a microscopic tug of war. If an equilibrium system is resting happily and we suddenly subject it to a stress, like, say, adding more of a chemical or messing with the environment, the system doesn't just sit there and take it. No, it furiously fights back in the completely opposite direction against whatever changes we introduced. It'll shift its net reaction forward or backward until a brand new balance is established. A perfect everyday example of this principle is literally just opening a carbonated soft drink. Whenever you open it, you hear that familiar hiss, right? Well, what you're actually doing is drastically lowering the pressure of carbon dioxide gas in the empty space above the liquid. The dissolution equilibrium is suddenly super stressed out, so to fight this change and replace that lost gas, the system violently shifts. It forces the dissolved carbon dioxide straight out of the liquid, forming those bubbles you see rushing up to the surface. So there are three major stresses we can apply to manipulate this tug of war. Number 1, we can change the concentration by adding or removing chemicals. 2, we can change the pressure or volume, which shifts gas phase reactions toward the side with fewer or more moles of gas. And 3, we can change the temperature. But hey, this is highly important to note here. Changing concentration or pressure just shifts the reaction around to satisfy the existing K value. Only changing the temperature actually alters the mathematical value of the equilibrium constant K itself. That's a huge distinction.
Okay, Section 4. Solving with ice tables, calculating shifts.
I'm going to slow down just a bit here, because this three-step toolkit is arguably the most powerful algebraic weapon a chemist has for predicting concentrations. It's called the ICE table approach. ICE stands for Initial, Change, and Equilibrium. It's just a brilliantly simple grid that helps us map out the before, the during, and the after of any chemical reaction.
Let's look at how this actually works in action. By setting up this grid, we place our known starting concentrations right in the top initial row. Next comes the change row. This is where we track the unknown shifts, which we represent by X. Now, the really beautiful part is that these X values are deduced straight from the reaction stoichiometry. Like if one reactant goes down by X, a product might go up by 2X, depending entirely on the balanced equation. Finally, we just add the initial and change rows together to get our equilibrium expressions. And boom, we can plug those right into our K equation to solve for the exact final concentrations.
Now, if you're sitting there wondering why you should take away this specific math skill or when you're literally ever going to use an ICE table outside a classroom, well, consider the medical field. Computing these exact equilibrium shifts is precisely how pharmacologists ensure life-saving medications reach the correct therapeutic concentrations inside the human body. When a drug is ingested, it establishes multiple, super complex equilibria within your biological systems. Mastering this math literally saves lives.
And that brings us to Section 5, the driving force, Gibbs free energy.
So we've got to ask the deepest question. Why does the balance settle exactly where it does? The answer is standard free energy, represented conceptually as a literal valley. This is Gibbs free energy. No matter where a reaction starts, whether it's super heavy on reactants on the left or heavy on products on the right, it will spontaneously slide down the energy curve to minimize its free energy. It's constantly seeking the absolute lowest possible energy state. That flat bottom of the valley where the free energy is totally minimized, that is the exact point of equilibrium. That's the precise moment where our snapshot Q perfectly equals our destination K.
Because these two core concepts, thermodynamics and equilibrium, are mathematically linked by the equation standard free energy change equals negative RT times the natural log of K, we can do something really incredible. We can use energy values alone to flawlessly predict whether a reaction will ultimately favor reactants or products. Just looking at the math, a negative free energy change means K is greater than 1, so products will be abundant. On the flip side, a positive free energy change means K is less than 1 and reactants dominate. It's all connected.
So, by understanding that equilibrium is really just a relentless, predictable balancing act, you now have the exact mathematical tools to manipulate nature itself. Think about that. We can push reactions up valleys, we can shift them by changing pressure or temperature, and we can isolate products that the universe otherwise really wouldn't want to yield. So I want to leave you with this. If mastering this dynamic math allows us to dictate the terms of chemical reality, what seemingly impossible reactions, materials, or cures will we force into existence next? Keep asking those big questions, keep looking at the data, and we'll see you in the next explainer.